of coherent signals, or so we'll go to the extreme case. You have a source S of t, which also gets lots of multipaths. So all the signals that arrive, even though they look like different, they are not different signals, right? Of course, their arrival angles are different, but any one of the signal is a delayed version of the other signal, right? Just a delayed version. And of course, this is narrowband. The delay will pop out as a phase. And moreover, there could be some scattering here, right? Scattering coefficient or reflection coefficient. So this is completely coherent because any two signals only differ in a complex multiplication, a complex attenuation, right, or amplification. Right? So remember, our previous model was x of t is equal to a s of t plus nt, or rxx is a rss A transpose plus sigma squared I when the noise is uncorrelated.
Our definition of S seems to be different than the previous case, right?
Well, I'm saying one signal, this is not a vector, just one signal coming at, this is S1, this is S2, SK, signals coming in. But anyway, SK, if you look at the SK, a difference, it is just a delayed version of S1, that's what it is. And maybe there is an attenuation here, yes. So think of SK is what is popping out of here, right? Then each of them will hit first sensor, second sensor, etc. And that's as before. So that's why I used this model. So if you look at the covariance matrix in the completely coherent case, so if I put this S vector, which is S1t, S2t, etc., skt, this is going to be S of t multiplied by alpha 1, alpha 2, etc., alpha k, right? Yes? This tau, I mean, you can use a different value. Just this is not the tau we were earlier comparing. It's just the path difference, right? Sk. So this path difference. Look at here. The argument is this path difference will come out as a will come out as a phase difference, and this is what I'm going to call it as alpha k. So it has got both the attenuation and the path loss, etc., path delay, etc. But the whole point now is, if you look at RSS in this case, this is the extreme case, completely coherent. Expected value of ST transpose is simply alpha transpose, right, multiplied by whatever is the power of this. But the whole point is the rank of RSS is now 1. So as I was saying, in the V2V, vehicle-to-vehicle communication, if you're trying to find out from a vehicle what are the other sources out there, you transmit a waveform, that's all. So everything is coming from different vehicles, but it's this scenario, completely coherent thing. So extreme case is 1. So in general, if you have some sources coherent, then the rank will be less than or equal to k. But we can start with completely coherent case. So you can say in the previous, this is not going to give you, everything will be erroneous, right? If you look at the eigenvalues using the previous argument, so the eigenvalues of Rxx, this will be of all sigma squared. This is rank 1. So what's the rank of this whole thing? Anyone? Yeah, use the Sylvester's inequality exactly the same way. The rank of this whole thing will be again 1. not k. That's the problem, right? So the eigenvalues are not going to, eigenvalues will be like this. One eigenvalue, and then the rest of them will be all equal to sigma squared, right? So we will erroneously conclude there is one source. So the previous method, there will be, of course, eigenvectors corresponding to the noise will be m minus 1, but they are only going to be orthogonal to this alpha vector, not the a's, right? So if you look at capital Rxx, that's going to be a alpha star A transpose plus sigma squared I. So you can see if I call this to be a B matrix, A alpha will be what? Another vector, right? Beta. So if I call A alpha, A is a matrix, so that will be beta. So this will be P beta transpose. So you can see the rank of the signal part will have only rank 1. So what is beta? Beta is, of course, A alpha. That means it is sigma alpha k, A omega k. Alpha k is here. A omega k's are the true DOAs, right? So this problem I see that has more relevance now. So some of you should, once I explain the technique known, then see whether you can, even if a couple of you work on the same thing, it's fine. But and so you get an unknown. This is, of course, these are unknown. So you get an the true directions, linear combinations is projected through one vector, and this is the only vector we will be able to identify. So the method fails.
Sigma squared, we can do it still with eigenvalue.
Yeah, no problem, right? So that's what I'm trying to say. If you plot this, when you see, so we are exploiting this, the fact that it is flat, that we conclude it as sigma squared. So we can subtract sigma squared. So all we can say is the eigenvectors corresponding to those noise orthogonal vector eigenvectors are orthogonal to beta. So we can find beta, but beta is only a linear combination of the. And here everything is unknown. K is unknown, alpha k's are unknown, and omega k's are unknown, the true directions, the theta k's. So that's where we are. And so if you consequently what it says is, look at here, and this may not be, so if you do so we can figure out beta. So if you do the output general, if you do beamforming or anything, so the signal, beta of course may not even correspond to a direction, right? Beta is a linear combination of the directions, right? So if you do beamforming, it's going to be, remember what is beamforming? A transpose RA, so beta transpose A. A is just the DFT of beta. That's going to be, that may not peak anywhere. It will give you, some output may give you something like this. Because this is, beamforming is what? A transpose RA. That's the same as beta transpose A omega squared. A is a generic, you're plotting against all omega. So that's not going to give you omega 1 through omega k.
Would it still peak a bit at each omega?
Could be, maybe not. Because there will be also cross terms. Remember, this A will hit this one. So it's AK transpose A. When you absolute value squared, you get the peaks, you get all sorts of cross terms, right? And they may merge and you may get a picture like this, or as you say, you may get something of this sort also, right? But you can clearly simulate this and see, right? So a method that has been proposed and works is called spatial smoothing. So the idea here is let me use the notation. So in order not to confuse, I'll use M0 sensors, and the number each size we'll use it as before. So this is a subarray. This is the first subarray, second subarray, and nth subarray, right? Each subarray is using, so the first subarray is using sensors 1 through M. Second one is using 2 through M plus 1, 3 through M plus 2, etc. And last one is L subarrays. Is this right now? L0. Is that right?
Just L2. If you got L subarrays, you start from L.
So from L to N plus L, supposed to be
Or this way, if this is M0, look at this entry is where? That's correct, right? Because each has got M sensors. You're right, this will be equal to L, right? So you get
Yes, it's correct. There are two sensors in the last subarray.
So look at here, R is RXX, or R1 rather, is what we had here. Let me take P to be 1, the signal source. So this is A alpha star, A star plus sigma squared I. That's because if I call this to be x1, x2, remember x1, x2 are vectors now. So x1 is A S of t plus nt, and x1. Yeah, first one is, remember, M sensors. That's the reason I used M. So this is the same as exactly the same structure, right? So S of t, this is the same as A alpha ST plus NT. And if you look at the Lth sensor, Lth subarray, see this is the first one. Second one, all happens is now you have shifted by a phase of e raised to minus omega 1, omega 2, etc., right? Right? Each source is going to create, if it is each source is going to create a phase shift, right? So consequently, RL will be A, B, L minus 1, alpha transpose, B transpose L minus 1, A transpose plus sigma squared I. BL minus 1 means there will be an L minus 1 here, right? That's the whole point of erasing a matrix, right? It's a diagonal. So this will be, I hope you see that, look, if you take the Lth array, if this is the Lth array, there will be only a phase shift, right? Corresponding to this one. This will be, right, for the kth sensor. So now the idea is you smooth it. As the name says, you do this. And what we are going to show that this matrix will take care of it will decohere the sources. So this is going to be A, so 1 over L, summation L equal to 1 through L. B L minus 1 alpha star B star L minus 1 then you have A star sigma squared I, right, because of the 1 over L. So let me call this matrix to be RS. I will call it with a something on the head so that you don't confuse this with, this is not RSS, I'm just causing overall. So this is going to be RS tilde. The smoothed version is 1 over L equal to 1 through L So I can write it like this, right? Alpha alpha star plus B alpha, alpha star B alpha, right? So notice that this is of the form like half V V star, right? So the rank of this you can see is equal to rank of V from the same familiar arguments, right? So not half, L, I'm sorry. So let me call this to be V. Look at its size. Remember, this is all K by K. So the maximum rank can be K, right? And this is K by L, right? V is K by L. So V is going to be
Is K bigger than we know the relation between K and L?
we need to find out, right? So let me write this as 1 over L V V star. So once we figure out the rank of V, we can figure out the rank of this, right? So V is just this piece. So that can be written as so here let me call this, just to be easy notation, nu I to be e raised to minus j omega I. Right? So remember, B is here. B is this entry, right? So if you multiply and stack all this, remember alpha is alpha 1, alpha 2, etc. alpha n vector. This is a diagonal vector. So I can rewrite this as in terms of this Vandermonde matrix. So if none of this, of course by assumption none of these alpha k's are 0. So this is rank K, right? This matrix is rank K. Anybody, what's the rank of this? This is a Vandermonde structure. Have you heard of this? If this is, you can see from here, so long as the directions of arrival are not the same, each of these rows will be what? Linearly independent, right? By its structure. So if it is square, what is its rank? If it is square, the rank will be the full rank, right? If it is square. But here size is K by L, right? We want, look, what is the goal? So we'll go backward. We want this to be rank, full rank. If it is full rank, all the previous theory will apply, right? We want this to be rank, that means we want the smooth matrix to be rank K. That means we want this matrix to be rank K, right? Because look here, this is rank K, then Sylvester's inequality will give you that the rank of that is, if V is rank K, then RS tilde is rank K. And look at, this is rank K. This is rank of minimum of K comma L, right? Yeah, so you get L should be, what did you say? Yeah, L should be greater than or equal to K. And where is the previous relation here? L should be greater than or equal to K. That will give you the number of sensors required. And remember, previously we said M itself is what? M should be greater than K. So this will be, you need at least twice the number of sensors from there. So if L is greater than or equal to K, the rank will be, this rank will be K, this rank will be K. Again, you can use Sylvester's inequality. Rank of V will be K. So rank V will be K if L is if and only if L is greater than or equal to K. So this is so if M is greater than so you get this, right? If M is greater than K, then if you have coherency, then you need see if it is uncorrelated, you need just K plus 1 sensors are enough. If it is completely coherent, this is the penalty you pay. You need more sensors to collect the data so that you can do the smoothing. You need to pay something, right? If you have problem, you need to, the price is more. So you just have to collect the data using more sensors. So now the question is, can you?
Sorry, what do you gain if you have more sensors than the C to have like twice M is enough, right? Twice M.
Yeah, I'm going to say, what is M? So let's say there are K sources, that's the way to go, right? Remember, if they're all uncorrelated, from the previous method we saw M need to be greater than K. So here you have, if you have coherency, then this is the new relation, right? M need to be great, total number of sensors need to be greater than the subarray size. This is subarray size previously, and then plus this. So, but each of this need to be greater than K.
Yeah, so like 2 windows are enough, right?
Yeah, you mean twice the number, yeah, right. So that's the penalty, twice of K, not twice of M.
Yeah, twice of K is enough. But like, what if you go beyond that?
I mean, you put 3K sensors, you mean? Remember, generally you're trying to do with the minimum job, I mean minimum number of sensors, because each sensor could be expensive and there may be no space to put it and etc. So you don't want, more the merrier. Of course, then you have to deal with the noise, but
The resolution will be more.
yeah, resolution will be more provided you do things correctly, right?
So could you repeat why in this case M should be bigger than K as for each subarray?
No, I mean, with the coherency, that's the relation, yes or no? No, I'm saying go back to the first case. So by doing the smoothing, we have decorrelated the sources. Yes? Why? Because this rank is this is now here we had rank 1, right? Somewhere here we had rank 1. We made the middle piece now full rank. So we have decohered the sources. They have become from the coherent situation, they have become correlated somehow, right? So now if you use the previous, you do a eigen decomposition on this matrix, smoothed matrix, it's going to have its eigenvalue decomposition will be, so again let me use a tilde for smoothing. So this eigenvalues will be like this now, right? Eigenvalues of lambda was, original R was like this, right? So this was the eigenvalues of R, original, coherent, just one. Now what happens is with this, this is the eigenvalues of R tilde. This is for R tilde. These are eigenvalues. So here you can find out the tail will have sigma squared, right? Because it is full rank. So the number of the sigma squared will repeat m minus k times the same argument. So the eigenvectors corresponding to noise eigenspace is going to be orthogonal to the vectors in this, which will be the direction vectors. So you can find out the directions of arrival of the coherent sources, right? So what is the penalty here? The penalty is the total number of sensors need to obey this equality. So each subarray, for this to work, m needs to be greater than k. Why is why? Remember, we went through this previous.
But previously we had each of the arrays to be
Greater than k.
Here just the sum is full rank, so I don't see how you're getting it. So we mean like R difference.
No, hold on. This what is the size of this array? M by m, right? Because each of the subarray, look at here, each subarray is 1 through m, 2 through m plus 1. The subarray size is m plus m by m, right? Covariance matrix. We are summing that up. That is still size m by m. So this matrix is m by m. And so there will be only m eigenvalues in both the cases, right? But the red eigenvalues will, the eigenvalues corresponding to R will all be sigma squared sooner, and whereas the black one will come, and that will also be sigma squared, but that will come only at k onwards, right? But then the penalty is you need more number of sensors. But remember, m need to be greater than k, right? So m naught need to be greater than 2k, right? So, which makes sense. Another, if there are issues, you need to pay some penalty. So the question is, this may be too extreme. Is it possible to reduce the number of sensors somehow? So you can do a little more squeezing. So this is called, this is of course, if you see, this is forward smoothing. So then the idea is that you come from the other direction. This interestingly works. So you start with this data, etc. Except, so I'm going to call, whatever we have done, I'm going to call this forward. Okay. So the forward data has this structure. This is forward. This is of course forward. And obviously this is backward, right? Again, I'm going to use arrays of size m. And since we know the signals coming at it, the interesting thing is if you so remember what we are doing. We take the backward, we collect the backward data, and then we complex conjugate it. So let me write this for you so you look at it. So this complex conjugation is important. I'll tell you why. So it's a column vector, so just to write it out, just to save space, I wrote it like this. So look at when L equal to 1, so you start with entry here, previous entry, etc. Except each data is being complex conjugated. This is complex conjugate, complex. So previously, remember, previously we were taking the data directly. The XL of t was XL plus 1, etc., right? Up to L sensors, right? L plus M minus 1, I suppose, right? Here I take the backward data and transpose it. Why am I doing this? If you do that, see, if you didn't have this star, there will be star here, etc. So complex conjugation. So to avoid that, we want this to look like this. So if you take the star here, then the key is you will get the A back here. And so I can simply define this to be some other set of coherent signals. So you can see the covariance matrix corresponding to the backward data, you can see from here is going to be A, BL minus 1, then some rank 1 matrix, right? Because whatever is the covariance matrix corresponding to this, BL minus 1 star, A star plus sigma squared. Here gamma is expected value of UT transpose. And so we have L equal to 1 through L. So you have the forward covariance matrices and the backward covariance matrices now. So as you can imagine, I am going to take so this is the forward covariance matrix, right? Forward. So let me define R double tilde to be, so this is our R forward, right? So we'll take the average of the forward and backward. So you can see this is going to then give you a structure like this. Previously we had alpha, so again, we have to concentrate on this, which is so I take the forward smoothing and backward smoothing and create a overall smooth forward backward smooth to covariance matrix. Now we need to see what is to make this, we want the rank of this overall smooth matrix to be K. So what is the condition on it? So I'll quickly do that and we will wrap this up. So as before, if you write this up, so let me call this, so RS double tilde so V is already here, right? We have a structure V like this, and V and D, let's say.
This should be B power L minus 1 or B power L? Previously we had
Yeah, this is all L minus 1, isn't it? Yeah. So V is here, and D is also going to be except a different vector, that's all, right? So you can also write like this as multiplied by its conjugate transpose. So once again, you need to concentrate, let me call this matrix to be E, so this is EE transpose. So we just need to concentrate on E to be to conditions on E to have rank, full rank or rank equal to K. So if I write E, so this is the previous space, right? This is our, this is like dV, and this is another diagonal piece. I'm going to call it D1, D2V, right? Yes? So this is like, remember, V is your van der Monde, right? One, nu 1, etc. Nu 1 to the power L minus 1, 1 nu 2 to the power. So F, of course, you can see is D1 inverse D2. But that will be another diagonal matrix, right? For example, gamma 1 over alpha 1, etc. Right? D is alpha 1, alpha 2, etc. alpha k.
What is that?
D1 inverse D2. I just pulled out, look at here. I just pulled out this, each of this piece, as we had before, right? Remember? This piece can be written as D1 multiplied by V. This piece is some other diagonal multiplied by V. Then you pull out D1. Then you get V comma D1 inverse D2 V. So that's because it's, this is, so F is, I just for notational convenience, it's a diagonal matrix. So again, let's look at the size. E is what? What is the size of E? K by, so this is full rank, right? So we don't have to worry about this. So we just, this is K by L. This is K by L. So this whole thing is K by 2L, right? So you can see unless in general, if the alpha case and gamma case are arbitrary, you will have a 2L, this will be K by 2L. So the rank will be, 2L need to be greater than or equal to K, right? Right. So the condition is for E to be full rank, we need E to be rank K. For rank E to be rank K, we need 2L to be greater than or equal to K. This is the condition. And what was the condition on L before? What was it? M naught was?
M naught minus, M naught was greater than or equal to M plus K.
In terms of L.
Oh,
M naught is equal to L plus M minus 1.
you have to go there, but
This is the one, right? Equal to.
Yes.
L is what?
M is bigger than equal to K again.
M is greater than or equal to K. So what do we get?
M naught is bigger than equal to K over.
L is greater than K by 2. 3K by 2. So we get a slight advantage, right? So if you're willing to do both backward and forward, you can reduce the number of sensors from having 2K to 3K by 2. So this is the most theoretically interesting solution. And some of the things I skipped, there are these constants could arrange in some way so that so this is only almost always. If these constants are, in general, this will, if these are all different, then this is true. But there are some peculiar situations where this will generate a degeneracy. But ignoring that, in general, this is at most, let me put it this way, this is the at most savings you can, or minimization you can achieve for the overall array when all the sources are coherent, right? So we dealt with uncorrelated signals, and now we gave one solution to the how to decohere or decorrelate the sources to find out the directions of arrival.